Hello, we are going to show you a demonstration of running real-time analytics on an OLTP system with database in memory. My name is Andy Rivenis, and I'm a product manager for database in memory. This demonstration was put together by Jorgen Miller and Edgar Schill, who are part of the Oracle Real-World Performance team. This is Oracle's Safe Harbor slide, and just says that you shouldn't make any purchasing decisions based on the information provided in this presentation. The purpose of this demo is to show that with database in memory, real-time analytics are not only possible, but can be supported with no impact to OLTP performance. This eliminates the need for separate analytic systems and can provide customers with information not previously possible to obtain because of the high workload requirements of running analytic reporting directly on their OLTP systems. The demonstration itself will show how running a high OLTP or transaction workload combined with running an OLAP or analytical workload will not affect OLTP transaction response time. The OLAP workload will be run with database in memory enabled and disabled to show the performance impact on the OLTP workload. The demo has been created using Oracle Database 12c Release 1 with the 12.102 patch set installed. This allows the use of database in memory, which is an option to Oracle Database that was introduced in 12.102. The database is run on Exadata, but we disabled Smart Scan to provide a more commodity-like hardware environment. The application workload was created using 4 Exalogic nodes as the application servers. The workload they generated on the database was then captured using Oracle Real Application Testing, or RAT. This allows playback of the actual database workload on a repeated basis, which is what we do in the actual demo. The application itself is based on a real third-party vendor application package that supports a true mixed workload environment, that is, OLTP and OLAP workloads. The transaction used for the OLTP workload are based on actual transactions and data used at a customer site, and the OLAP reports duplicate the reporting that is required to be run on a separate reporting database because of the concern over the impact to OLTP workload. The bottom line here is that this simulates a real-world application workload that an actual customer might want to run. For the demonstration, we have separated the OLTP and OLAP workloads so that we can control their execution. The OLTP workload runs for the entire time. It is composed of 6,400 users that run one of a set of transactions every 10 seconds. The total OLTP workload is therefore fairly constant and can be observed in the demonstration between the OLAP workload periods that we will describe next. The OLAP workload is run for approximately 10-minute periods, alternating between running with database in memory enabled and running with database in memory disabled. This was done to show the benefits of database in memory for the OLAP workload. The workload itself is made up of 20 connections that randomly run one of 100 reports. These are run with no think time in between submissions, so there are always 20 of these reports running during the steady state of the OLAP run period. It is important to note that this test was purposely architected not to exceed the CPU and I/O resources of the machines involved. This allows us to review the performance strictly based on resource usage with essentially no contention or queuing. This prevents any randomness in the response times or resource usage and allows the demonstration to show the true potential of database in memory. Now let's switch to the actual demo. Here you see an Enterprise Manager view that shows the demonstration as it is running. I will describe all the components of the workload in the next screen, but I wanted to point out the following as an overview. The demonstration itself runs for approximately an hour. During that time, the OLTP workload runs continuously. As we said in the previous slide, the OLAP workload runs either until the first of the 20 streams completes, the in-memory enabled case, or until the timeout of 10 minutes is reached, the in-memory disabled case, first with in-memory enabled and then with in-memory disabled. These OLAP periods show up in the average active sessions section above as large resource usage. At the very beginning of the test, there is approximately a 20-minute ramp-up period during which the database will be flashed back and restarted. The tables will be populated into memory. The RAT replay will be started and the OLTP users will connect and begin executing their transactions. During this time, the OLTP workload will reach a steady state without causing a large spike in the initial startup. Now we're going to switch back real quickly to the presentation so that I can describe what you saw in the top of the average active sessions chart from the EM Performance Hub screen that we were looking at. I will describe what is going on in each of the time periods, so hopefully it will be a little clearer how the demonstration is run. Let's start by taking a look at the leftmost side of the chart. As has been labeled, this is the OLTP ramp-up period. Again, it takes approximately 20 minutes to get all 6,400 OLTP connections made and executing transactions. The steady state is approximately 1,300 transactions per minute. Notice that at the top of the chart, we have labeled a box with OLTP workload consistent rate. Underneath that box is a chart that represents the transaction rate for the entire demonstration period. We also have two arrows pointing down to the circled areas. This represents the OLTP steady state rate and shows up between the OLAP time periods as a constant OLTP workload is being run. Below the chart, we have two boxes with charts illustrating what is happening during the OLAP time periods. The first, or leftmost, period shows OLAP workload being run with database and memory disabled and the OLTP workload. The chart below the labeled box shows the breakdown of the resource usage, and notice that it shows user I/O and CPU as the main resource usage. This makes sense since we have disabled the use of database and memory. In the next period to the right, we see OLAP with in-memory and OLTP. Here, database and memory has been enabled for the OLAP workload, and now we see almost no user I/O, and all of the database time is consumed by CPU. This shows what the different aspects of the average active sessions charts are showing us during the test. Keep in mind that we haven't yet discussed the rate of the work that is completed during these periods. We have just shown the resource usage patterns for the connections or users during the different testing periods. Now we will switch back to the Enterprise Manager screen and drill down a little deeper into each of the OLAP time periods, first with in-memory disabled and then with in-memory enabled. Notice that we have selected the Monitor SQL tab and we'll move the EM slider to an OLAP period with no in-memory. Once the screen refreshes, it shows us the most expensive SQL run during the time period highlighted by the slider in descending order. We chose the highlighted SQL because it appears high on the list in both the time period without in-memory and with in-memory. In the live demonstration, you can choose any SQL you want, or even two different statements to compare. You will notice that all of the statements have a user I/O and CPU component in the database time column and are performing I/O, that is, see the I/O requests column. And all but the longest ones have runtimes in the 2 to 3 minute time range. We can investigate the actual SQL Monitor Active Report by clicking on the SQL ID link, and we will take a look at that in the next screen. Here we see the actual SQL Monitor Active Report for the SQL statement with the SQL ID that we chose on the previous screen. Notice that this execution ran for 2.9 minutes and consumed both user I/O and CPU in the database time section. If we look at the execution plan section, we see that Oracle performed full table scans for the tables VBAP, NARA, and LIPS, and that the majority of the database time, see the activity % column, was spent scanning two of those tables and then performing a hash join. Now let's look at an OLAP time period with database and memory enabled. We'll move the average active session slider over to that time period in the same screen as before, which is the Monitor SQL tab. Notice that now most of the SQL executions are dominated by just CPU time in the database time column, and that their durations are significantly shorter than what we saw with database in-memory disabled. Now they're on the order of 20 to 40 seconds. Also note that the SQL ID we chose shows up towards the top of the list, but now only runs for 45 seconds. Let's drill into that SQL statement and look at what the SQL Monitor Active Report shows us now. Once the SQL Monitor Active Report displays, we will see that we are now accessing the three tables in memory, that is, table access in memory full, and that we are using a Bloom filter with one of the hash joins. We also see that almost all of the database time is spent in the outermost hash join and hash group by statements. What this means in practice is that we have run significantly faster and used significantly less resources than with database in-memory disabled. And as we will see in the following slides, we can run a lot more OLAP reports in the same time period than we could without database in-memory enabled. So let's switch back to our presentation and summarize what we saw with the workload. The OLTP workload is a mixture of select, insert, and update statements. These statements are taken from a running application at a customer site and then run with simulated user connections. The response time fluctuates slightly based on the load, but stays relatively constant with little noticeable concurrency or capacity constraints, as evidenced by the average active session screens. There are a total of 130 unique OLTP SQL statements, and each of the 6,400 connections runs approximately 100 in a randomized fashion, once every 10 seconds. The actual transaction response time fluctuates anywhere between approximately half a second and 2 seconds. The overall database workload during the demonstration is also tracked through an Apex application. The following shows the OLTP transaction rate, that is, the OLTP transactions per minute, the average OLTP transaction elapsed time, and the average OLAP queries run per minute. We've selected a time period during the demonstration that shows just a single period for OLAP queries with in-memory enabled and with in-memory disabled, along with the corresponding time between periods to show just the OLTP workload. In this next screen, we've highlighted the section that corresponds to the OLAP period with in-memory running disabled. Notice that although the OLTP transaction rate remains relatively constant, the elapsed time or response time degrades, and that only a relatively few OLAP reports get run because they take so long. In this screen, we highlight the time period between the OLAP periods, and we see that the OLTP response time returns to a steady rate and that no OLAP queries are being run. And in the final screen, we see the OLAP period with database in-memory enabled. And this shows that the OLTP response time now stays steady and does not degrade. And we see that many more OLAP queries can be run than could be run without in-memory enabled. To summarize the effects on workload, the OLTP workload rates averaged about 50,000 transactions per minute and didn't fluctuate appreciably with no OLAP reports running, with in-memory enabled OLAP workload, or with in-memory disabled OLAP workload. Since the database server capacity was never exceeded, this provided a nice control for the testing. The OLAP workload rates with in-memory disabled ran at about 19 reports per minute, and some didn't finish within the time period and had to be stopped. The OLAP reports also consumed a significant amount of CPU and user I/O, as evidenced by the average active session screen and SQL Monitor active reports. The OLAP workload rates with in-memory enabled, on the other hand, were able to run at about 192 reports per minute and used almost all CPU with very little user I/O. To conclude, this demonstration shows that in a real-world application scenario, it is possible to run real-time analytics using database in-memory on the source data and not impact the existing OLTP workload. It does require sufficient CPU resources, but by not impacting the I/O subsystem, it makes that analytic workload more scalable while providing significantly better response times. This also avoids having to create a separate reporting system and can allow the business to get answers without having to wait for data replication, or ETL. Database in memory truly delivers on the promise to provide real-time analytic performance in a mixed workload environment.